It's going to be a tired afternoon for me. So then we went on, we studied a little bit of kinematics and rotational motion, and we learned that pretty much the equations are the same as translational. If you're moving in straight lines or whatever, you get these equations that work out as long as you have a constant acceleration, where you can calculate different things. You also have the average velocity equation down here. But the same thing happens in rotational motion. Instead of x, we have theta. Instead of v, we have omega. And instead of a for acceleration, we have alpha. So theta is the amount of angle that you rotate through. Omega is how much angle you're rotating through per second. And alpha, of course, is the acceleration, angular acceleration. So if you're accelerating your rotation, you have acceleration. So the equations are the same. You use them pretty much the same way. Remember, with kinematics, what you want to do is you want to look for equations that will give you the thing that you don't know using the things you know. And sometimes you have to use 2 or 3 equations, but that's basically the idea. It's not really that complicated. And then we moved on to dynamics. Rotational motion, where instead of having force equals mass times acceleration, we have torque equals mass time, torque equals rotational inertia or moment of inertia times rotational acceleration. So this is our new Newton's law. Instead of force equals mass times acceleration, torque equals I times alpha. Right? And of course, you can rearrange that to solve for alpha. Or you can even rearrange it to solve for the rotational inertia or the moment of inertia I. But remember that the moment of inertia was dependent on more things than just the mass. It depends on where the mass is, kind of what the shape of the mass is, and also depends on how the mass rotates. So here we give you some formulas to calculate some simple moments of inertia from some simple shapes being rotated on certain things. But another thing that you need to remember is that if you have multiple objects being rotated around the same axis, you have one point of rotation, but multiple things rotating around it, then you need to calculate the moments of inertia for each of those things using this chart and then add those moments of inertia together to get the total moment of inertia. And this was the example of that, where we start off with just a merry-go-round, so we just have a disc, a flat disc, and then later on we put a child on the merry-go-round, so this would be a hoop would be like a child going around an axis, and you had to add that moment of inertia to the moment of inertia for a disc. We could even go further and add the rails onto this. The rails on this are like things that are they're like tubes that are being rotated around their center, and that's kind of like this one right here, a tube or a rod being rotated around its center, right? And you could add on the pipes that are sticking up over here, and they're kind of like adding little children in each section here. You'd have to know the mass of the pipes and everything else, but you wouldn't have to do anything for the center because it's at the center of rotation, so it's not going to have any R, it's not going to have any distance from the center, in other words, and it will not contribute much as long as the radius of that center tube is quite small. If it's not quite small, then you would add another moment of inertia from this one, the solid cylinder. So you could you could even add the second disc along the bottom if it has a different mass. You could add that on because it has a different radius for sure. But in the end, the idea is that you can add moments of inertia to get a more complex moment of inertia from a more complex object rotating about an axis. Then we move on now to energy, rotational energy. We covered this one as well a little bit. And they actually work through, no pun intended, calculating the work of rotating an object. And if you do that, you end up with an equation that looks like this. The net work equals I omega squared minus 1/2 I omega squared minus 1/2 I omega initial squared. And this looks a lot like the force energy equation, the force kinetic energy equation, where you have the net force equals the difference in the kinetic energy. In other words, if you apply a force to an object over a distance, you're going to get that object changing its speed. It's going to create a change in speed there. And so we define the rotational kinetic energy as 1/2 I omega squared, where omega, of course, is the rotational velocity of the object. And we didn't get around to actually doing these examples, so let's go ahead and do them. We have the work and energy for spinning a grindstone. So the grindstone is let's see. Yeah, so we're going to start the grindstone at 0, I guess, and we're going to speed it up with a force of 200 newtons. And this 200 newtons, she's going to push on the edge of this stone for 1 radian of angle. Right? And then the radius is 0.320 meters radius at the point of application, and friction or negligible. We're going to say friction is negligible. We want to find out the final angular velocity, so how much work, final angular velocity, and final rotational kinetic energy. So the work done, the net work is going to be the torque times the amount of angle that it goes through. And we know the amount of angle. They say that it's 1 radian of angle. So that theta there is going to be 1. How much torque is it? Well, the torque is going to be from this 200 Newton force. You have the hand pushing on it with a 200 Newton force, or pulling on it either way. With a 200 Newton force, what is going to be the torque from that 200 Newton force? Well, it's going to be 200 newtons times the radius, the distance from the center, which is 0.320. So that's right there, radius times distance. The angle, of course, is going to be 1 radian, so that we plug that into our work equation. We get 64 Newton meters of work, 0.320 meters times 200. So that's the amount of work done. The net work is 64 joules. Part B is to find how much it's sped up, essentially. Right? You want to know what its final angular velocity is. Well, you can use the kinetic energy. We can use the kinematic equations. They're going to use kinematic equations with an initial angular velocity of 0. And they're going to solve this equation where we know how much angle it goes through. We know the angular acceleration. And assuming we know the angular acceleration, no, they don't tell us the angular acceleration. We're going to have to calculate the angular acceleration. So we find we use the net torque equals net torque equals I alpha, or alpha equals net torque over I. To do that, that's not a serious problem because we know the torque already, so we're good there. We also calculate the moment of inertia for a disk from that table of all the different shapes, and plug those two numbers in, and we can get the alpha. Not the only way to do it, but that's one way to do it. Once we've got our alpha, we can plug it into our kinematic equation and get this. This is a long mess of stuff. Right? It's a lot of stuff. Why do we need to do all that? At the very beginning, we calculated the net work. And back here, we said that the net work is equal to the change in kinetic energy. If our initial kinetic energy is 0, that means our net work is equal to our final kinetic energy, 1/2 I omega squared. We could use this equation right here to solve this problem. And we wouldn't have to do all those steps and use 2 equations. Net work, we know. We just calculated that. I, we can calculate. That's not that hard. Omega squared is what we're trying to calculate. We want to know. We want to know omega. So we could do that. And then we would get the same answer. It turns out we would get the same omega, 5.42 radians per second. They went the long way to show you how to use kinematics, but you can use energy and go the short way. Either way, it's up to you. If you want to do more work, you're more than welcome to follow this example. And then once you know that omega then you can calculate the kinetic energy. The final kinetic energy is right here, and this kinetic energy is 0. Right? And that's all rotational kinetic energy, part C. Here they calculate a helicopter's rotational kinetic energy inside of its rotors. Rotational kinetic energy is 1/2 I times omega squared. And if this helicopter has 4 blades, and they're each 4 meters long, and they each have a mass of 50 kilograms, then we can approximate the blades as thin rods that rotate about one end of their axis. Now that shape does exist in our little shape thing here. If we go back to our different shapes, different moments of inertia for our different shapes right here, you see we have a rod that is rotating around its end. That's this one right here. So that's kind of like one blade on a helicopter. If we calculate that for one blade, then we can multiply it by 4 and have all 4 blades. Just like adding 4 of them together. So we have 4 blades. Here we go, 4 helicopter blades, all using. We're going to use this equation to calculate the kinetic energy. We're calculating the omega from they tell us RPMs, or revolutions per minute. So we just convert that into radians per second. And then the I, the moment of inertia, is 4 times the ml squared over 3, and that's what it is for a rod rotating around its end. You've got your I for all 4 blades there. You plug in the numbers in the rotational kinetic energy. 5.26 times 10 to the 5th joules of energy, and you're good to go. Then they want to know what's the translational kinetic energy, right? 1/2 mv squared is the translational kinetic energy for, let's see what they're asking here. Calculate the translational kinetic energy of the helicopter when it flies at 20 meters per second. So 20 meters per second, the kinetic energy of the helicopter moving forward is 2 times 10 to the 5th joules, but the kinetic energy of the blades holding it up is more than double that. 5 times 10 to the 5th, right? 5.5 times 10 to the 5th. It's almost triple. So the amount of energy in the helicopter blades is much more than the amount of energy in the helicopter itself. The blades are the things you got to be careful of, right? That's why people duck when they go on a helicopter. To compare kinetic energies, you just take a ratio, and that's what they do. At a maximum height, all rotational kinetic energy will be converted into gravitational energy. So essentially what helicopters are designed to do is they're designed to turn all of their rotational kinetic energy into height, into potential energy. So if you start off with 5.26 times 10 to the 5th joules of rotational energy, that's how much energy your helicopter will have in potential energy. So you set that number equal to the mass of the helicopter times g times h in part C, which is what they do right here. And it turns out to be 53.7 meters when they solve for the height. And this is one of the reasons that helicopters can't go very fast, because they use they're using a lot of their energy to keep themselves up. The way that a helicopter goes forward is it tilts itself forward and it uses some of its blade power to move forward, right? That's how most helicopters work. There are some helicopters that are actually designed, almost all of them are military helicopters. Some of them are designed with forward propulsion available to them in addition to their helicopter blades. So, but those are usually military helicopters. Those can go much faster. But if you want to go fast with a helicopter, you actually have to give up some height. So you have to tilt the blades forward and use some of that energy to get going fast instead of going high. So this is one of the classic examples of using this this energy, these energy ideas, rotational and translational energy ideas, in a situation. This is kind of like the rolling down the table race that we did yesterday, or whenever it was we did it. In this case, we're going to calculate the final speed of a solid cylinder that rolls down a 2-meter high incline. The cylinder starts from rest, has a mass of 0.75 kilograms and a radius of 4 centimeters. We have to know the radius in addition to the mass in order to calculate how fast it's going to be going. We start off with energy at the top of the hill is all potential energy. M times G times H. It's not rolling, it's not sliding, so there's no kinetic energy. It's all potential energy. It's just energy because it's up there. At the bottom of the hill, all of it is going to turn into kinetic energy, but there are two kinds of kinetic energy. The one kind of kinetic energy is its movement, how fast it's moving forward, 1/2 mv squared. That's how fast the cylinder is moving forward. And then there's 1/2 I omega squared, which is how fast the can is rolling in angle per second, right? Omega. And this is our rotational kinetic energy. We have to put in both of these on the right side. But we have a problem. That is, we were trying to solve for the velocity, v right here, but omega is an unknown. We need to solve for omega in terms of velocity. So instead of omega in here, we put v over r in for omega. We end up with v squared over r squared, right? We also have to plug in I for the can, or for the cylinder. I for a cylinder is 1/2 mr squared. So they got to plug that in for I. And now we've got an equation that has everything in it that we know except one thing. We don't know v. It's v squared here, it's v squared here. So we go ahead and we solve it for v squared. We throw away all the m's because it's the same m and everything. And then we've got a v squared in two terms. Add them together. We get this is our answer in the end, our solution for v. And we're plugging in our numbers. But it does take into account this and this. If you just calculated this for a can that was sliding down the hill, the same can, but it's sliding down the hill with zero friction, it will actually go faster at the bottom. Because all of the potential energy at the top will be turned into linear energy, kinetic energy at the bottom. But in this case, some of it's turned into linear kinetic energy, and some of it's turned into rolling energy. In other words, it takes a little bit of energy to get the can rolling, as well as moving forward, right? There's an advantage to having wheels, and that is that it makes it easier to push something along. But there's also a disadvantage to having wheels. Wheels steal some of your kinetic energy. Some of the energy that your car uses to get going has to be used to actually make the wheels roll. And that's kind of like wasted energy. And now we come to angular momentum. It turns out that angular momentum is actually the only kind of momentum that is conserved. Linear momentum is conserved in two-dimensional and one-dimensional collisions. As long as things don't start to rotate. If things start to rotate, like if you have one car that comes in and hits another car, and the cars start turning and twisting after the accident, then linear momentum is no longer conserved very well. However, angular momentum is always conserved. So it turns out that when we say conservation of momentum, we're actually meaning this. Well, what is angular momentum? Angular momentum is the amount of momentum that something has from rotating or turning, or even just going past some random point. Everything has angular momentum. And it turns out that the formula for the angular momentum looks a lot like the formula for linear momentum. Instead of momentum equals mass times velocity, it's angular momentum. We're going to use L. Remember, in momentum we use P. We're going to use L for angular momentum. And that's going to equal our moment of inertia, I, which is dependent on mass and shape, and omega, which is the angular velocity. So how fast something is spinning, you could think of that, right? So let's calculate the angular momentum of the Earth. I equals 2. So for a sphere, for a solid sphere, the moment of inertia is 2/5 mr squared. So for the mass of the Earth, for the Earth's moment of inertia, we would use the mass of the Earth, the radius of the Earth squared, of course, and multiply by 2/5. So that's going to be a big number because both the mass and the radius are huge numbers of the Earth, right? This is going to be the moment. In other words, the moment of inertia of the Earth is humongous, which means it's very difficult to get it spinning and it's very difficult to stop it from spinning. That's why the Earth has been spinning for so long, actually. Then angular momentum is going to equal this I that we calculate up here times the omega. We plug in all our numbers, mass and radius and everything else. The angular velocity of the Earth, which is, the Earth goes around on its axis once every 24 hours. We're going to have to make a conversion there. And they go ahead and do all the conversions here. Here's the, this is the, so the 2/5 is the 0.4, of course. This right here is the I, this is the mass. This is the radius, right? Got that, so that's the 2/5 mass times radius. And then they're doing that in revolutions, times 1 revolution per day. So that's right, okay. No, we're missing the I. Where's the I? Oh no, this is the I. It's right here. Never mind. So we got it. We're calculating now. Then they convert the 1 revolution per day. So they do all this math, call that revolutions per day, and then they're going to convert the revolutions per day right here. 2 pi rads per revolution, 8.64 times 10 to the 4th seconds per day. Right? That cancels out the 1 revolution per day. You get 7.07 times 10 to the 33 kilogram meters squared per second, which is an absolutely enormous angular momentum. That is absolutely humongous, right? But what that means is that it's very difficult, the angular momentum, the momentum that something has is directly related to the amount of force that is required to get it to that momentum or the force required to stop it from having a momentum. So if you have a huge momentum, that means it's extremely difficult to stop. And that's exactly what the Earth, it's absolutely true that the Earth will stop spinning at some point. At some point, the Earth is going to stop spinning, unless something else happens to it. Then probably that happening to it will make it stop spinning too. But it's going to take forever unless something cataclysmic happens. Like, it might stop spinning if the moon runs into it, right? And it wouldn't stop it spinning, but it would slow it down a lot more. Maybe it might even speed it up, depends on which way the moon hit it. But something really big would have to collide, would have to exert a force on the Earth in order for it to stop spinning. And it started spinning 5 billion years ago, and it's been doing it ever since. Hasn't really slowed down appreciably. It's hard you could hardly notice how much it's slowed down really since it started. So how do you slow something down or speed something up that's already spinning? You apply a torque to it, and that torque is going to cause a change in momentum over time, just like force has caused a change in linear momentum over time. So here's our equation for torque as it relates to momentum or angular momentum. Net torque equals change in momentum over change in time. And here's an example of this. We have this Lazy Susan, the spinning table, and we're going to exert a torque on it to make it start spinning. We want to see if the food can go flying off. Right here, they tell us the force, they tell us the radius, they tell us the time. They want to know what the final angular momentum is if it starts from rest with no friction. So we have a force. The force is going to create a torque. The torque is right there in the equation. It's the only torque because there's no friction. It's going to equal the change in momentum over the change in time. We know the change in time. And we know that the change in angular momentum is equal to I times omega, I times omega. So the moment of inertia times the angular velocity right there, I times. So what we do in this example is we go ahead and we have our alpha equals net torque over I. The net torque is going to be the force times the distance, or the force times the radius. Calculate that really quick. We calculate our alpha from our alpha is going to equal the net torque over I. So we go ahead and calculate that, 35.2 radians per second squared. And then they go ahead and use the kinematic expression to calculate the final angular velocity. Or you can use the kinetic energy to calculate that, because the kinetic energy equals 1/2 I times omega squared, and we know that the kinetic energy has to come from the work. So the work that we did, I'm in the wrong one. There we go. It's the same solution. Actually, we do a different solution. Here we go. So here we're calculating we have our change in L and net torque over change in time. That's faster than the last one. Sorry for that. But that net torque is equal to force times distance. Same idea, right? Force times distance. Plug in our numbers, and then that angular momentum that we calculate is also equal to I times omega. Solve it for omega, get L over I. So this is much faster for this, because they're solving for the right thing. We plug in our numbers and we're good. It's just, I mean, we're doing the same kind of things. This is the equation you need to remember. Instead of force equals change in momentum over time, you need to do torque equals change in angular momentum over change in time. Same idea. But you need to remember that torque is also equal to I times alpha. Whenever you're dealing with torque, remember that it can be equal to two things. Change in L over change in T, or it can be equal to I times alpha. Just like force can equal change in momentum over change in time and mass times acceleration. Because usually you can get the force from one of those two, and then you can calculate the rest of it from once you calculate the force. I just get lazier and lazier, and I just get my slouch down in my chair, tired. Here's another example. This is the knee kicking one. You're kicking your leg. You exert a 2,000 Newton force with this muscle right here, and it pulls back right here. And the perpendicular lever arm is 2.2 centimeters right here, 2.2 centimeters. And that's how much, you're gonna use that distance and that force to calculate the torque that's being applied. And then we have the moment of inertia of the lower leg. They just tell us what I is right there. And then we can find the angular acceleration, because torque equals I times alpha, right? And they just tell us. They've told us the force in the R to calculate the torque. They've told us the I. We can just multiply those together on the top to get the torque, and divide by the I that they give us to give us the angular acceleration of 35.2 radians per second squared. Then they use that in a kinematic equation to solve for omega, or you can use well, actually they don't. Yeah, you can definitely use that. And then you can, once you've calculated the angular acceleration, you can plug that in and calculate the kinetic energy of the rotating leg, and you're done. I mean, it's same kind of stuff that we've done before. It's not any different. It's not any different in the math. It's just different in recognizing what rotational things go into the equations instead of linear things. So, conservation of angular momentum. The initial angular momentum is going to equal the final angular momentum as long as you don't have any forces that are going to transfer momentum out of the system. So things like friction cause a transfer of momentum out of the system into the earth or into something else. things like that. Just outside forces acting on the system can either speed up the system, speed up its rotation or slow down its rotation. If they're not accounted for, you get in real trouble. But this is the idea that initial angular momentum equals final angular momentum. Or I times omega equals I prime times omega prime. And you see this all the time with dancers, right? Dancers and skaters and all kinds of people, it's divers, and in fact, just about all athletes take advantage of this regularly. I didn't ever start my Zoom. But if you have a dancer, let's say that you have a skater or whatever, a diver or whatever, you have this person who is, let's say they're starting off with their hands and maybe one of their legs sticking out, right? So there's my stick dancer or skater. And because they have all they have all these appendages sticking out from them, that actually gives them a very big eye. So their moment of inertia is quite big when that happens, because their mass is far away from their center of rotation, which is up the middle of their body, right? So they have a really big eye, and if they have an angular momentum of L, like this, then I times a big I times a little omega will give you this kind of L, maybe. But what happens if they take and they scrunch in their leg so that their leg is not sticking out, it's tight in, and then they fold in their arms so that their arms are really tight in too? That's actually going to make a really small I. And what happens to their rotational velocity? What happens when a skater brings in their arms and legs after they've been sticking them out? What happens to their rotation? Do they get bigger or smaller? More rotation or less rotation? Come on, haven't you ever seen the Winter Olympics? So you start off with your arms out and your legs out, right? And then you bring them in. 308 RPM. Natalia somebody. Right?
Three ways this backflipping black figure skate.
So what happens there, is the omega becomes huge as the I becomes small. If you bring all your mass towards the center, then your omega becomes huge. Why? Because the angular momentum was conserved. This has the same angular momentum as this one, but this one has a much higher angular speed than this one, or angular velocity than this one. Why? Because the other one has a much higher a much higher moment of inertia, right? So rotational inertia matters. It matters where the mass is. So if we have a skater that is spinning at 0.8 revolutions per second when her arms are extended, and she has a moment of inertia of 2.34 when her arms are extended, and then she brings her arms close to her body and she has a moment of inertia of 0.363, how much faster will she be going? Well, moment of inertia, angular momentum will be conserved. That means your initial momentum equals your final momentum. That means your I omega is going to equal your I prime omega prime. They tell us the I and the omega, and they tell us the I prime, but they don't tell us the omega prime, so we solve for that. And then we just plug everything in and we're done. 5.16 revolutions per second when you pull in the arms, after you started with less than 1 revolution per second. But is the kinetic energy conserved? Let's see, rotational kinetic energy is 1/2 I omega squared. So at the beginning it's 29.6 joules of kinetic energy. At the end, I prime omega prime squared, we plug those in, we get 191 joules. Kinetic energy is not conserved here. We start off with 29, we end up with 191. So where did that energy come from? How did she get more energy into her spin? How could you possibly add energy? Did someone come in and spin her? What could have possibly added energy to this skater's spin? What happened between the slow spin and the fast spin? What happened?
Would that be when she brought her arms in?
That's right. She actually had energy stored in her body. And that energy stored in her body is in the form of biochemical energy. It's food that's been turned into these chemicals in our bodies, right? And she used some of those chemicals, she broke some bonds in those chemicals to pull her arms in and to create a higher energy. So she converted energy in her body into energy in the spin. And if you've ever skated or danced, you know that it takes energy to do that. It's really hard to go from a slow spin to a fast spin. It's very difficult. Pulling your arms and legs in is not easy. It requires a lot of energy. In fact, that accounts for probably about half of the energy that skaters use when they're skating. About half of their energy is pulling their arms and legs in and out. And the other half of it is jumping and pushing things like that. But it's a lot of energy. And this is why, this is why skaters are generally pretty dang skinny. It's because they're burning all this energy all the time. They're constantly arms in, legs out, all these things. So, anyway. This is actually how solar systems are formed. It's a very similar thing. You start off with this big disk of just junk floating around in space, spinning around and around and around. And gravity starts to pull it together towards the center, and eventually there's a star formed in the center. And out towards the edges, gravity starts to pull other pieces together, and you get little planets. But eventually, you have this solar system that has kind of been created from all this stuff. Now, not all the stuff is going in the same direction, it turns out. Sometimes the stuff is going both directions. In fact, always stuff is going both directions. So every once in a while, you get a planet that's going in the opposite direction. We have a planet that does that and has retrograde motion. You even have planets that spin in opposite directions sometimes. I think it's Uranus that has retrograde motion, or maybe it's Neptune. I can't. Okay, so that's conservation of angular momentum. Now let's talk about collisions. Now we're going to have, instead of just two things moving in straight lines, hitting each other and then bouncing off in straight lines, what happens if we have something that's rotating or something that's turning that collides with something else? And then we have a collision and we have motion after that. So here is an example where we have a board nailed to a table, and then so it can swing around, it can rotate around the table. And then we throw the board around and it rotates around and it hits this little hockey puck thing here, right? How do we calculate how fast that ball is going to go compared to how fast the stick was going? Well, it's a conservation of momentum problem. We have angular momentum in the stick to start with, then it hits the ball, and the ball actually gains momentum. But we're going to deal with the momentum of the ball as an angular momentum, even though the ball, the puck, whatever. The puck actually will probably go forward in a straight line. That's the likely scenario. That is the very likely scenario. But we can still calculate an angular momentum from it because it is moving with respect to this point of rotation of the board. So we want to know the angular velocity of the two after the collision, ball and stick, and we want to know the kinetic energy before and after the collision, the total linear momentum before and after the collision. So the first thing is the angular velocity of both ball and stick. So angular velocity is remember that angular velocity is how fast something is moving relative to a point as kind of a rotational reference. So we're going to do this using the angular momentum equation. Angular momentum is going to be preserved, so the initial angular momentum equals the final angular momentum. Before they hit, only the stick is moving. So it's just I of the stick times omega of the stick. The I of the stick is going to be mr squared. That's what it is on the chart of a stick moving around its axis. And then the omega is going to be the velocity of the end of the stick divided by the radius of the stick. And we're gonna do that so that we can get a velocity in the end here. So this ends up being our final equation. It simplifies to just m times v times r. After the collision, after the stick hits the puck, the stick will be moving and the puck will be moving. Oh wait, I'm doing this backwards. Sorry. This is actually the ball. The puck is moving first, and then it hits the stick, and then both the puck and the stick are moving. I did it backwards. I said the stick hits the puck, but it's actually the puck hits the stick. So this is actually the equation for puck hitting the stick. It's the same equation, it turns out, and that's fine. But, so this is the I for the puck times v over r for the angular velocity of the puck about the point where the stick will rotate around. So this r is still the radius of the stick, and this r is still the radius of the stick because we're using the stick as our reference for radius. Then the final one is going to have momentum of puck and momentum of stick, right? And so we're going to have a moment of inertia for puck, that's mr squared, and then the moment of inertia for the stick, which is mr squared over 3 for a stick. And then we add them together for the total final moment of inertia because they're actually going to stick together. They say that they stick together. And so there's our final moment of inertia. And then we use it in this equation right here, where we have the initial equals the final. We have an I omega on each side. And we solve for the final, omega, yeah, right here. And we find out that they're going to go 1.74 radians per second afterwards. Now this should be slower than the original. The original was, let's see, where did we calculate that? We calculated right here. The omega, they actually calculated here, or omega equals v over r. So the velocity of the ball originally is 30 meters per second divided by r, which would be 1.2. So it's a little bit under 30 meters per second, and it ends up going 1.7. So it's a little under 30 radians per second. It ends up going just a little under 2 radians per second. So it's a lot. There's a lot of loss of angular speed there. Then they want to know the kinetic energy. So we have kinetic energy of the ball. This is 1/2 mv squared for the ball. But afterwards we have rotational kinetic energy of ball and stick, and they calculate that I omega squared. We already calculated the I of ball and stick. We just plug in the omega, 1.744 radians per second. We get 1.57 joules. So start off with 22.5 joules of kinetic energy, and you end up with 1.57 joules of kinetic energy. So kinetic energy definitely not conserved here. And then the linear momentum before the collision is just mass times velocity. It's 1.5 kilogram meters per second. And afterwards, if you calculate the linear velocity, just using the tangential velocity of stick and ball, stick and puck or whatever, get 2.2. So linear momentum is definitely not conserved. Linear momentum actually goes up. And the whole point here is to recognize that the angular momentum is conserved. At the beginning that works just fine, but the kinetic energy, not the same before and after. The linear momentum, not the same before and after. Only angular momentum is conserved in reality. So this is related to lots of things in sports. We have this idea of the sweet spot of a baseball bat or a tennis racket. How many of you have played tennis or baseball or softball before? You know what it's like when you hit that ball perfectly right on the right spot of the bat? It just feels right, right? And it sounds right. But if you hit it too far to the end or too close in, what does it feel like? Feels like your hands just got smacked, right? It really hurts because what happens is the bat has rotated in your hand. So if you hit the bat if you hit the ball just at the right point on the bat will rotate. It will just continue to rotate around your body, but it will not rotate in your hand, right? And it's designed for that. It's designed to do that. It's designed on purpose that way. Because all things can rotate around something, they just deliberately design a bat or a tennis racket so that it will only rotate around the body and not around another axis on the racket if you hit the ball in the right place. And they do that by shaping the racket in different ways, by distributing the weight on the racket in different ways, by having the racket or the bat be a particular weight for a particular shape, for a particular swing. You know, it's very, very, it can be very customized, in fact. So you have, you know, you and me, when we want to go play a sport, we go pick out a racket or a bat from a sports store somewhere. Or you have somebody like, you know, Roger Federer, who goes into an imaging room and swings his racket a million times against a ball. And Wilson actually takes a gazillion different measurements and they custom build the racket for him. So his racket, you know, compared to, if I buy the Roger Federer signature racket, it costs me $300. His racket probably costs 10 grand to design and build or more, right? Because of this. It's designed specifically for his swing, for his body, for the way he does things. Very few people have that done for them. Pretty much only the very top people in every sport. You know, you have 10 or 15 or 20 of them that have that done for them in tennis, another about that many done for them in baseball. You know, you had, let's see, who was the last person I knew who had a bat designed specifically for them? I'm sure there's been a lot, but I haven't been following baseball. Barry Bonds definitely did. Barry Bonds had a bat company that made his bat specifically for him. And in fact, very few people in the major leagues could even swing his bat. So it was so heavy. It helps to have a little bit of your performance-enhancing drugs to swing that bat. Anyway. Okay. So lots of interesting things, lots of interesting science goes into sports. It's kind of fascinating, in fact. Like one of my favorites is that there's a bicycle company that very few people have heard of. It's called Specialized, and it's my favorite bike company, actually. And they actually partnered with Ferrari Formula One Racing to design their bicycles for their top racers. Specialized has designed the winning bicycle in like 90% of the races in the world for the past 40 years. So they're definitely a top bike company. But now they're using Ferrari's techniques for using carbon fiber to build things. And actually Ferrari's using some of their techniques too. It kind of went both ways in the end. But they, these bikes that come off their pro line, they already sell a $20,000 bike that anybody can buy. You can buy a $20,000 bike from Specialized, and it's a super high end bicycle. But if you're one of their top performers, if you're one of their top professionals, they'll spend $50,000, $80,000, $100,000 on your bike, which is just outrageous. These bicycles that cost as much as a house, but they win. You don't make a lot of money cycling in the United States, but in Europe, it's a huge sport. There's just tons of money that goes into cycling. Okay, so now there's something very interesting about angular momentum that we haven't taught you yet, we haven't really explained to you. And it has to do with the direction. Torque is a vector. So let me find a little device here that we use. Let's see, where's my, a really good rotated steel somewhere. Where do I put it? Okay. Can I ask you to be my volunteer? We usually like to have the smallest person in class because it gives us the best demonstration. Go ahead and take a seat there, put your feet up on that. And then hold this right there and see how easy you turn here. So, turn your back. Now what we're going to do is we're going to spin the wheel in your hand. I'm going to put a camera on you so anybody else who watches this can see what happened. Change camera. How do I change camera? I forgot. New share. Video, select camera, Microsoft. Where's my other camera? Here it is. All right. Okay. Smile, you're on camera. Okay, so what I'm going to do is I'm going to spin this thing really fast. And what I'm going to be doing by spinning this thing, be creating some angular momentum in the wheel, right? So it'll have a lot of angular momentum. That angular momentum has a direction. It's pointing somewhere. And you're going to change the direction it's pointing by turning the wheel. Because if you turn the wheel while it's spinning, that will change the direction of the angular momentum. Okay? Ready? You have to hold up a little higher so you can turn it. And to turn it, you can either turn it this way or you can turn it this way. Either way you want. Now turn the wheel. Now turn it once, one way, and keep turning it that way. Okay, let's do it again. Do it the other way. Go the other way. Well, it's not turning the wheel. Why is it not turning the wheel? Okay, let's try a different one. Usually that one works better than this one, but let's try this one. This one is a little more difficult because you don't have a place for your feet to go. So you kind of have to just tuck your feet up under the chair. Let's see everyone on the screen. We need to switch the screen to a bigger screen so everybody can see. Let's try that. All right. Put you just in here. There we go. All right, ready for this? Put your feet up, try not to touch the bar underneath there. Now turn it the other way. Okay, you can see that. Now I turned your chair, right? Turn it back. Okay, good. Now let's put it straight up and down again. I'll give it a little more turn. Now instead of turning it sideways, I want you to turn it this way. I want you to turn it this way or this way. Okay, back to the way. Back to the way. Okay. So it has a weird effect, right? So turning it sideways caused the chair to rotate in a different dimension. Like we're rotating this way, we're rotating this way, and then we're rotating this way, and it causes a rotation this way. This is rotation, and this rotation, and this. It's a weird effect. It's a very weird effect. And it took a while for people to figure out what's happening. And what they did was quite creative, actually. What they did is they assigned the direction to the momentum, or to the angular momentum. They said, well, if this wheel is rotating this way, so right now it's rotating. Let's see, I'm going to cause it to rotate this way. So it's rotating around this way. I started it down this way, right? If it's rotating that way, how am I going to save the angular momentum? What am I going to say about the direction of the angular momentum? What I'm going to do is I'm going to use my right hand, and I'm going to take my fingers and I'm going to curl them in the direction of the rotation. So the wheel's rotating down this way, and I'm curling down this way. My thumb is going to be the direction of angular momentum. So the angular momentum is actually pointing out this axis. It's actually pointing out the direction of this axis, right? And you can see every time I move it, it actually makes the wheel do funny things. If I move it this way, it actually pushes it down. If I move it this way, it actually pushes it up. That's not me. That's the wheel. I'm just trying to move it sideways. It moves it down. If I try to move it sideways this way, it moves it up. Weird, right? So apparently my angular momentum is pointing towards the whiteboard, pointing towards the camera there, right? And if I try to change it, if I try to move it so that it's pointing right, it tries to go down before I can get it back up again. Right. Why would it do that? How would that have anything to do with anything? So it's pointing this way. I try to move it this way, and it goes this way. Why? Well, what am I actually doing when I try to move it to over here? What I'm actually doing is I'm adding some angular momentum around my body this way. I'm rotating my body this way, right? And that's like a rotation. So if I use my hand to my rotating body this way, to look at my momentum, I'm changing my momentum downward. Right? So it's like I'm taking a momentum that starts out this way, and I'm trying to change it that way. And what I did was I added a momentum that way. That's weird. And it goes down. And it's, you have a similar thing with this when you have your momentum going like this, and then we turn it sideways like this. So if I turn it this way, my chair tries to rotate. When I turned it this way, my chair tried to rotate this way. Let's see which. I do that again so I can feel it. If I rotate it to my left, the chair tries to turn to the left. If I rotate to the right, the chair tries to turn to the right. Right? Why? Well, my angular momentum starts out this way, and then if I try to turn it that way, it's like my angular momentum is going down. It's going from sideways to down all of a sudden. And why? Why does it make my chair turn this way? It's kind of weird, isn't it? Confusing. But guess what? They figured it out. The direction of angular momentum is conserved. Nature is essentially trying to compensate when you change the angular momentum. It tries to compensate and conserve that angular momentum by adding another one. So here's the example. Then. Which way is my angular momentum pointing? Left, right? If I try to turn it to the left, it makes my chair kind of jerk to the left, like this, which means it's adding an angular momentum that is up. But if I turn it this way, I'm actually changing my angular momentum to down, right? It was pointing this way, then I tried to change it to down. And what did this angular momentum do? It tried to push it back up. It tried to add another angular momentum up. So this one was going this way, and I tried to turn it down, and the turning of the chair gave me an angular momentum up to compensate. That's the conservation of angular momentum that's happening. And all rotating objects have that same kind of behavior, where if you try to change the spinning axis of an object that is spinning, something around it or itself will react in a way, something that is connected to or itself will react in a way with some other kind of spin to preserve that original angular momentum. And that can be used to figure out which way you're going. That's used all the time. They built these devices that have 3 spinning wheels in them, one in each direction, right? And anytime you turn, that thing will tilt or turn. And they're called gimbals. And when they tilt or turn, however far they tilt or turn tells you how much you turn, what change in direction you have. They put these things in submarines, they put them on spaceships, they put them on boats, they put them on all kinds of things. And on submarines, they have ones made of lasers. In fact, instead of having with spinning wheels, they have lasers that go around and around in a circle with mirrors, and they're very, very precise. And that, just on that alone, you were able to go under the ocean and know exactly where, if somebody knows exactly where it is, to within a few hundred meters. That's how accurate they are. They can go for months underwater, and just using that gimbal, just using that device, and know where they are pretty much every time. It's pretty amazing stuff. So anyway, that is one of the consequences of the vector nature of angular momentum. Oh, I hope that actually showed over the video. I don't know if it actually did. Well, yeah, it should have, actually. Should have showed just fine. Okay. So anyway, here they actually show those three. There's your original vector, and the vector from the turning of the chair or whatever is turning the wheel, and how they add together. Here is a gyroscope. You may have seen one of these before. A gyroscope uses these things. In fact, a gyroscope is often called a gimbal. And that takes us to the end of the chapter. All right, so we are done with chapter 10. Let's take a look at our calendar and see what's coming up. We have a test coming up, right? So we have homework 10 and then exams 6 through 10. When are you guys planning on taking the exam? Do you have any plans in particular for taking the exam? Any day of the week that you think that you might take it? Not sure yet? Okay, that's fine. Trying to think of anything else we need to talk about. I can't think of anything else. We definitely want to get done with homework 10 as quickly as possible because we want to start chapter 11 and finish chapter 11 next week. We still have 12. We have, I can't remember how far we have to get through here. We have 12, 13, 14, 15, 16, 17. So we have 7 chapters left and 4 weeks left. 7 chapters, and we'll have one. When is the last day of class for this class? I think it's the last day of July or something close to that. If I can remember my password, it'll be amazing. Hey, it's amazing. All right. Holy mackerel, that's a lot of classes. Wrong semester. That's more like. Let's see, last day is 8/1, so first day of August is our last day of class. So we have 1, 2, 3, and then 4 weeks after this week to cover 7 chapters in 7 chapters in 4 weeks. So really we want to be done not only with chapter 11, but maybe even chapter 12. So fluid statics and dynamics in a week, we could probably do that. Heat and temperature, and heat transfer, we could probably do these 3 in 2 weeks, and then these 2 in a week pretty easily. Yeah. But it'll be a little bit crammed at the end, but this stuff at the end is easier. We're going to essentially, after chapter 10, we're going to leave everything behind that we've done so far. For the most part, we won't be doing anything with vectors or anything with, we'll be doing stuff with energy still, but no vectors or kinematics and stuff like that. And we're going to be learning some new things, but they're, I think, easier for most people. We start off with fluids, and then we'll do heat and temperature, and then we'll go on to waves and sound, and we'll crank those out. So if we can, we'll try to do we could even try to do a little bit of chapter 11 today, but we definitely want to get through 11 and 12 by the end of next week. So let's get the calendar. Where is chapter 12? Oh, this is chapter 12. It's just been labeled wrong. So if we did chapter 11 here, maybe. Here, 13, and then we hit like 14 here and 15 here or something. And then 16 and 17 the next week will probably be good. All right, so that's kind of where we're at. We'll do a review of, if you have any questions for chapters 6 through 10, we can answer questions like that concerning those things on Monday and Wednesday after we're done with chapters 11 and 12. Get you ready for your test. And besides that, we just, if nobody has any questions, we can entertain homework questions if you want. I know that there are some homework questions I haven't answered yet. So, does anybody have any particular homework questions they want to talk about for chapter 10? Or? I sent some replies to your questions, and I can continue to do that, but does anybody want to do any in class? Are you guys good for today? You want to do question 1? This one right here? Okay. All right. Well, this one is a little bit of review, kind of just rotational ideas. I just like it too because it's a space station and I'm a nerd. But so in this one, they have the space station that is, they're trying to put artificial gravity on, 9.8 meters per second squared. And they tell us the station is 145 meters in radius. And they want to know how fast it should spin. But then they say that's too fast. It was making people like freak out. So what happened if they spun it at only 16 meters per second? What would the radius have to be? So this is just remembering something that's quite useful to us, and that is the equation the centripetal acceleration equals tangential velocity squared over r. So that the tangential velocity is the speed that you're going on the edge of the circle, right? With the radius r like this, tangential velocity is out here, right? Where the centripetal acceleration, of course, we want to equal gravity on Earth, which is 9.8 meters per second squared. Man, that's terrible. I'm even worse when I'm standing up because I have to sit down to get the right angle. And now that my chair's at the right height, maybe I won't slouch so much. Okay. So then, so we start off with 9.8 meters per second squared, and they tell you the radius, and then you solve for the tangential velocity. And then in the second part, they tell you the tangential velocity, you solve for the radius. Just this equation twice. Anybody else have one they want to do? So this is another kind of review one. In fact, a lot of these are reviewed. They're not necessarily angular momentum ones. This one is because, so this one is, this one's a bit of a challenge because it has a pulley that has a radius and a mass to it. So this pulley is going to have a change in angular momentum as this block accelerates. And so there's, it's going to have you could think of it as a tangential acceleration, or I mean a rotational acceleration actually, where the block has a moment of inertia I and an angular acceleration alpha that is going to be related to the linear acceleration of the string or of the block. So this one you have two different things, and this is how I would recommend you think about this. Let me make sure that I'm thinking. So we have a block with this mass. It's accelerating as the pulley, as it unwinds the pulley. That has a cylinder with this mass, radius r. Consider the positively blocking down and the pulley rotating clockwise. So they're telling us to consider positive opposite we would normally would. So block going down and the disk rotating clockwise will be positive, we'll call it. And then they want to know what is the downward acceleration of the block. So when you're doing this kind of a problem, you definitely want to draw a drawing. So we're going to have our pulley, and we're going to label it with the radius r. We're going to label it with mass m, we'll call it little m. And then we have our string coming off, and we have our block, which we'll call big M. And there's going to be a couple of different things going on here. There's going to be an acceleration, there's going to be an angular acceleration here. So there's going to be a torque, in other words, exerted on this thing, and the torque is going to be equal to the angular, or the moment of inertia of this pulley times the angular acceleration of the pulley. So that's of the pulley and this is of the pulley, just so you remember that. The torque is caused by the tension in the rope. There's a tension in the rope right here. The tension is caused by this mass pulling downward, right? And so the torque is also equal to because it's being caused by the tension in the rope times the radius of the pulley, because that's being pulled right there. That tension is pulling on the pulley right there. So that torque is also equal to that. So this one ends up equaling the tension times the radius. Tension in the rope times the radius. The tension in the rope is also pulling up on the mass. And there's another force pulling down on the mass, which happens to be gravity. So this is mass M big M times G. And so from this part of the problem, we have another equation. The other equation is the sum of the forces equals the mass times acceleration. So they told us that gravity down was going to be positive, so we'll call that mg minus the tension in the rope, because they said that upward is going to be negative, is going to equal the mass times the acceleration. Now, this is what they want us to solve right here is the acceleration. We know the big mass, we know the big mass, we know the little g. We don't know this. We also don't know what the tension is up here in this equation. But we do know some other things up here. So let's figure out this equation up here really quick. I, for a rotating disc, if we go back to our book up here, go back a few sections to the section on shapes and their moments of inertia. Right about here. Then a disk rotating about its center right here is mr squared over 2. So we can go back and put that in, mr squared over 2 for my, so I is going to be the mass of the disk, that's little m, times the radius of the disk squared over 2, that's I, so right here is I, right? Then we multiply by alpha, but alpha is the rotational acceleration of the disk. So that means that alpha of the pulley is going to equal the acceleration of the rope, which is wrapped around the pulley, which is just A, divided by R. So instead of alpha, I'm going to plug in A over R here. So that's my alpha, A over R. And that equals tension times R. Well, look at this. This equation, we know the mass, we know the radius, we know 2, and we know R, right? We don't know A, but that's what we're trying to figure out. We don't know T, but that's fine, because what if I solved this equation for T and plugged it into this equation? Then I would have one equation with no T's in it, but just A's in it. And then I could solve that equation for A and solve for A and be done. And that's exactly how you do this problem. Solve for T up here. Plug it in right there. And then solve for A and be done. Tricky, huh? But physics is full of problems like this, and we'll be seeing even more of them. They won't necessarily be problems like this where we're using torques and everything else, but we will see plenty of equations like this going to the end of the class, where we have multiple equations that we have to solve one to get one thing, and then plug it into another to get another thing. right? We've seen them. We've seen plenty of them already, I guess. But this is classic physics. The algebra is actually the tricky part. Oh, and this is very much like the example that we saw in the book, where we start at the top of a hill with a mass, and this time it's a ball instead of a disc. So you have to use a different moment of inertia for this one. I is going to be a different formula. Go back to section 3, look at the formulas for a ball, and this we're going to assume this ball is a solid ball, I think. It's a mass of 4.4 kilograms. It has a radius of 0.07 meters, and then you calculate your I from that, and then you'll be able to calculate your potential energy at the top, and the kinetic energy at the bottom is going to be two different kinetic energies. You're going to have a linear kinetic energy and a rotational kinetic energy. Then you can calculate the final velocity, rotational and linear, at the end. Remember, the rotational velocity is related to the linear velocity because the ball is rolling and rolling. The speed that a fly would be on the edge of a rolling ball is the same speed that you're moving along the ground. You think about it, right? So you have your angular velocity equals your linear velocity divided by the radius. And and again, I didn't read the problem. In this problem, it's actually going up the ramp, so you have to do it backwards. You start with kinetic energy, rotational and linear, and then you end up with potential energy at the top. And that's how you calculate this, how far it will go up the ramp and everything else. But anyway, it's still that kind of a problem where you have kinetic energy of two kinds turning into potential energy at the end. Here is another classic. This is like an ice skater, except instead of the ice skater pulling their arms in, it's and having or putting their arms out and having a change in their moment of inertia because they put their arms out. We're just going to add another disc. So this disc is spinning with some speed, with some angular velocity, and then we drop another disc onto it. And that increases its moment of inertia. So you have to calculate the moment of inertia of this second disk and add it to the moment of inertia of the first disk. And then that's your final moment of inertia, and then it's conservation momentum from there. L times omega equals L times omega. This is another of the energy goes from potential energy to two kinds of kinetic energy, and so on and so forth. And some, I don't need to stop giving. Why do I give you 7 chances on this problem? It's just crazy. I need to stop doing that. So most of these questions are actually just conservation of momentum questions, where you have an L times omega to begin with equals an L times omega, sorry, an I times omega, I keep saying L times omega. You have I times omega equals I prime times omega prime. Your beginning momentum equals your ending momentum. And one of those things changes, which requires the other thing to change, and you calculate it. They're all fairly simple problems. Does anybody have any other questions? Any other specific questions for chapter 10? Problems that you want to go over? If there are no more questions, I'm done for today. You can call it quits. Have a good afternoon.